In the terahertz applications group, we're exploiting spectral properties of terahertz radiation. This is a part of the spectrum that's very beneficial properties for investigating materials, in that it is able to penetrate through materials that are opaque at visible frequencies, such as polymers, such as ceramics, such as semiconductors. So we can see the structure in these materials. At the same time, we can study molecular interaction, which happens also at terahertz energies within these materials. We can use terahertz imaging to look at coating structures by exploiting the fact that we can generate a short pulse of terahertz radiation, which can penetrate into the material of interest and reveal detail of the structure inside this material. We can look at structures as complex as pharmaceutical coatings, so polymer films that are applied to tablets to give them additional functionality. And we can look at samples in the automotive industry, for instance, where you also have multiple coating structures applied to a substrate, and you need to know in detail as to what the structure is at each point. We don't need direct physical contact between the sensor and the object of interest. And that gives us great versatility as to how we can apply this in technical applications.
We use terahertz technology to measure the porosity. Porosity is important for the pharmaceutical industry as it is directly correlated to the performance of the majority of pharmaceutical tablets. We send a pulse of terahertz radiation through a pharmaceutical tablet and measure the refractive index of this tablet. This refractive index is then directly correlated to the porosity of the tablet. On the other hand, we can use X-ray computed microtomography to measure the pore structure. Here we can analyze the pore shape, size and pore orientation of these pores inside a pharmaceutical tablet.
The thing that's really great about terahertz spectroscopy is we look at motions of molecules that occur on a bulk scale. So we're looking at big collective vibrations of molecules in the solid. These types of motions are related to things like solubility and stability of materials, and also properties such as semiconducting ability in semiconductors. All of these factors are related to how the molecules pack, and this is exactly what we can probe with terahertz spectroscopy. One of the key things that we do to understand exactly what these motions are is we use computational techniques to fully describe exactly what the individual motions are that we probe with terahertz spectroscopy.
One further exciting application of terahertz spectroscopy is to study amorphous materials. Those are materials where there's no long-range order. They can be used in many different industries and have been proven to have very desirable properties. But the one thing that limits their application at the moment is it's impossible to predict when they will crystallize. Using terahertz spectroscopy, we're able to unravel some of the fundamental dynamics of these materials, which leads to the crystallization. By developing this understanding, we believe that we can really further the application for those materials and the widespread use for those materials, thus enabling the availability of exciting new materials in the future.